Okay, so 8.2 talks about operations with matrices. So this is basically adding, subtracting, multiplying, and dividing these. So it covers determining whether two matrices are equal. As I mentioned, adding, subtracting matrices, multiplying matrices by scalars, and then multiplying two matrices, using matrices to transform vectors, and then using matrix operations to model and solve real-life problems. We're not going to do the vector stuff. You don't really need to worry about that. So we're just going to be focusing on the actual operations themselves. So I'm going to start with just equality of matrices and then the various properties of matrices. So two matrices are equal when they have the same dimension. And actually, it looks like my slides got out of order now that I'm looking at this. No, I just have a duplicate slide. Okay. We'll stick with it. Somehow I have an extra slide and I have this in two places. Okay, well, two matrices are equal when they have the same dimension and every corresponding entry is equal. So it's basically if you have two matrices, oops, having technical difficulties. Let me get my pen out. So if you have like a matrix, I'm just making it up here, and it's equal to another matrix, each spot has to also be equal. So that's the only way for two matrices to be equal. Now I could have something like instead of 2, I could have like the square root of 4 there. That's still equal to 2, so it's still equal. But basically every entry has to match in order for it to be equal. And that makes sense that it needs to be basically the same thing. So we do have some properties of matrix addition and scalar multiplication. I'm going to go into what doing the matrix addition and the multiplication, but the key thing is here that the properties of regular numbers, the commutative and associative property for addition, are true for matrices as well as real numbers. So the order that you add matrices does not matter. And then you can group different matrices together to add them up. So the order there does not matter for adding, or with subtracting, you just have to make sure you convert it to a negative. For multiplication, if you're multiplying by a number, then you can kind of group different numbers together. But note that there is nothing here about the order of multiplication. So multiplication of matrices is not commutative. And that's where you can flip-flop the order, where instead of like A times B, it's B times A. You can't do that with matrices. You can do that with addition of matrices, but you can't do that with multiplication. Multiply a matrix by 1, that just keeps it the same. And then the distributive or property does apply as long as you're multiplying it by a number. So those kind of seem they make sense that it has the same sort of properties as what we're already doing, and I'll demonstrate these, but you don't really need to know this too much because this is more into the linear algebra stuff. So linear algebra is a course on its own, basically studying matrices, and all you guys really need to know is how to multiply them and how to solve them. So you don't really need to know too much of the properties, but I'm going over it anyway, just so you have an understanding of how they work. So matrix addition. To add or subtract, you have to have the same dimension. So that means the same number of rows and columns. So I have an example here. These are both 2 by 2 matrices because there are 2 rows, 2 columns. So they have to have the same size. That 2 does not. There we go. So they have to have the same number of rows and the same number of columns in order for you to add or subtract them. And when you add or subtract them, you're basically looking at each element by itself. So the elements are what are inside the matrix. And so you add the matching parts. So like I've highlighted the 1 and the -2. So those are in the same location of the matrix. So when you add or subtract those are the ones that you add or subtract. So you do it element by element, and you just match it up the position. So I'm going to just color code all of these so that you can see what parts we are adding together and which ones are subtracting. So these are two matrices that we are subtracting, and normally you can just do this in your head, but I'm going to write it out. So you would have 1 minus -2. Oops, forgot my negative side. -2 for that first spot, so that's the yellow. And we're subtracting because I have a minus sign in between the two matrices. Then with the orange, we have -3 minus 5. Then green, that lower left, I have 0 minus 3. And then in blue, 4 minus -5. So you just treat each location like its own subtraction there. And the same thing would be true for addition. So then I just simplify. So 1 minus a -2 is 3. -3 minus 5 is -8. 0 minus 3 is -3. 4 minus -5 is 9. So when you're subtracting matrices, that's why you have to have the same dimension, because otherwise you wouldn't. You would have, if it was different dimensions, let's say I have the same matrix, and then I'm subtracting something. I'll use the same base, and then I'll add extra zeros or an extra row. If you have something like this in the bottom where there's an extra row, you don't have anything to match that row with, because you need to have everything matched. So this last row doesn't have anything in the other matrix to match it up with, so you can't do that subtraction. So you have to make sure that everything has something that you can subtract. Does that make sense? Do you guys have any questions? Next is scalar multiplication. So a scalar is basically just a number, a single number. I mean, we just normally call those constants or coefficients. In linear algebra, when you're dealing with matrices, you call them scalars. I don't actually know where that term comes from, but there's two different types of multiplication. There's scalar multiplication, where you multiply it by a number, and then there's matrix multiplication, where you multiply it by a matrix. So that's why they have different names for it. So scalar multiplication is you're literally multiplying your matrix by a number. And it actually, you can think it might be called a scalar because it scales it. It basically, every number in the matrix gets multiplied. So I've got two examples here. So that 2 in front, we multiply everything inside the matrix by 2. So that would be 2 times 1, 2 times -3, 2 times 0, and 2 times 4. So just everything gets multiplied by that 2 when you're multiplying matrices here. So that would give us 2, -6, 0, and 8. The second example, you have a negative sign. So that's just basically changing the signs. It's like you're multiplying everything by -1. So that would give you 2, a -5, -3, and 5. So scalar multiplication is pretty simple. You just have to multiply every number by whatever's in front. So that's not too complicated. This is where I put the extra slide on accident. So just some key notation about matrices. Whenever we work with matrices, we always name them in capital letters. And so that's how you know whether you're working with a matrix or not, because normally when we're solving equations, we have lowercase, like we have a lowercase x, y, and z. When we have matrices, we use capital letters. So that's important to know that that's the convention so that you're being clear that you don't use lowercase. Essentially, a capital O is the symbol for a matrix of all zeros. So it just means that everything is zero in whatever the matrix is. And I is the symbol for the identity matrix. So the identity matrix is always square, and then there's always 1 in the diagonal and zeros everywhere else. So I just gave an example of a 2 by 2. One is, you always have the diagonal going from the top left to bottom right. That's always the diagonal that we put it in. So that's the identity matrix. And then if you have a matrix and you're solving for variables, instead of using a lowercase, like when we solve for x, we use an uppercase x. So an example of a matrix of unknowns could be 1, x2, x3, because you have multiple unknown values. So we just use x and we just number them 1, 2, 3, that there's 3 different unknowns there. So that's just some important notation, just so that you know when you're labeling things on your homework, or there's a question about A times B, that you understand that these are matrices that we are multiplying together. Any questions so far? Okay. Oh, Ryan, that's a very emphatic no. Okay, so this is a little side thing that you don't actually need to know for any of the homework, but I think is really neat, a way to show you how matrices are sort of just like regular solving. So we have 2 matrices here, A and B. They're both 2 by 2 matrices because those are the easiest to work with. And we have this equation, but they're all, instead of with variables, they're with matrices. 9 times A equals 6 times B minus 3x. And you want to solve this, and you're looking for what is the matrix X. So when we use matrix notation, we can solve it just like we would solve anything else. So I'm not going to actually replace A and B with the matrices. I'm going to literally solve this equation for X just like I would solve anything else. So the first thing is to subtract 6b from both sides. So that gives me 9a minus 6b, and they're not like terms because the a and the b are different. And then that equals negative 3x. So I'm solving for x, so I need to get rid of that negative 3, which is just a scalar, just a number. So I'm going to divide everything by negative 3. So 9 divided by negative 3 is a negative 3, so I have negative 3a. Then negative 6 divided by negative 3 gives me a positive 2, so I have plus 2b equals x. So now x is an unknown matrix, so now this is where I'm going to plug in my matrices so that I actually can figure out what x is. So I'm going to kind of move up to the right here. So x is negative 3 times a. So I'm going to replace a with the matrix. And then plus 2 times b. So I'm going to replace b with its matrix. So now we're going to do our multiplication first before we do addition. It's the same order of operations that with solving anything else. You know, we're just following the order of operations. So when I multiply negative 3, I have to multiply it by everything. So that's going to be a 6, negative 3, positive 3, and 0. And then I'm going to multiply 2 through the second matrix, 0, 4, 6, and 0. And then we basically just add these matrices together. So I just add each like location with its matching. So 6 plus 0 is 6. Negative 3 plus 4 is 1. 3 plus 6 is 9. And 0 plus 0 is 0. And so that's our matrix. So the point is that even though matrices look different and they have multiple elements in there, the same rules of algebra apply. Because a matrix is basically, you think of it as you've got multiple equations, but same rules apply. So you can add them, you can subtract them, you can solve for something, order of operations apply. And this skill, you may not need it in this particular class, but oftentimes if you have programming classes, I know not everybody's doing programming, but we do have people that are in computer science. And a lot of times you store data as an array or a matrix, and then you have to do some manipulations. You have to multiply that data by a number or, solve something. So a lot of times when you're programming, you actually are working with matrices and solving equations like this, even if you're not doing it by hand. Are there any questions about that example? All clear, cool. Okay, so matrix multiplication. This is what you have to do on, I think it's problem 2 on the assignment. This is the part where it gets a little confusing for people. So when you're multiplying matrices, you have to have the inside dimensions match. So the inside dimensions, I'm calling these two parts that I've highlighted. So an example would be if I have a 3 by 5 matrix, and then I'm multiplying it by another matrix, it needs to be a 5 by something. I don't care how many columns it needs to be, but it needs to be 5 rows to match with the 5. So this is row and a column. So if the first matrix has 5 columns, then I need to have 5 rows in the second one. So it really doesn't matter what the outside ones are, but the insides have to match in order for those to multiply together. And that's why it's not commutative, because if you try to flip-flop those, the insides don't match. And when you end up multiplying them, you end up getting a matrix of the outside dimensions. So if the outside dimensions here are M and P, that is what you end up with your result. So if I have this 3 by 5, let's say a 5 by 7, my resulting matrix is going to be 3 by 7. There will be 3 rows and 7 columns. So it's sort of like the inside smushed together, and then that's the size of the matrix that you have resulting. Now, when we do the multiplication, what you do is you go row by column. So you have like first row times first column, first row by second column. So it's like a regular multiplication table where you do a row times a column, but there's multiple entries, so you end up adding them together. It'll make much more sense when I start demonstrating this. Now, before I get to the demonstration, just some properties. So order matters. So there is no commutative property when you're multiplying matrices, but the associative property still applies. Distributive property still applies. You can still multiply them by numbers, and the number can either be multiplied by the first matrix or the second matrix, whatever is easier. But the key is that you can't reverse the order of multiplication. It doesn't work. So I've got 2 matrices here. So this first one is a 2 by 2. The second one has 3 rows, 2 columns, so that's a 3 by 2. So we're going to do matrix multiplication here. So we find A, B. So A is 2 by 2. B is 3 by 2. So the insides don't match. The rows and the columns for the inside parts, these don't match. They're not the same. So we cannot do this multiplication. because they don't match on that inside there. You have to have the number of columns of the first one match the rows in the second. But we can do B times A. So if you do it in the other order, B is 3 by 2, A is 2 by 2. So those insides match. So our result is going to be the outsides. We're going to get a 3 by 2 matrix out. So we're going to have 3 rows, 2 columns when we do that multiplication. So I'm going to write our columns. Actually, what I tend to do is write the numbers first, and then I fill in the symbol, the matrix symbols, so that I can make sure I have enough room. So B, and when you're showing your work, you have these brackets. That's how we indicate that we have matrices. I can still use the dot for multiplication, or you can use an X or whatever you want. And then A, 3, -4, -2, and 9. So this is we're going to be color coding. I'm going to try. So I'm going to take the first row and I'm going to multiply it by the first column. And so I'm going to, this will take up a lot of work when you're writing this out. So I've got -1. Oops, where's my, okay. Why is my pen not writing? Oops. Let's try this again. Okay, so I'm taking the -1 and then I multiply it by the 3. And then you add the next part. So the next one is going to be 4, and you multiply it by that -2. So it's the first value in each one multiplied by the second value in the next one. And then you would keep going. So if you had 3 times 3, you would then have to match them up that way. So that's how we get the first entry. So you're multiplying and adding to get this entry. So that is first spot. Then I'm trying to be very careful about how I'm multiplying. Now we take that first row and then we multiply it by the second column, and that will get you your next entry. So I have -1 times -4 plus 4 times 9. So we're going to get a 3 by 2. We're going to have 2 columns. So that's forming the second column. So take this -1, multiply it by that -4, and then you have this 4 by 9. That's how they kind of work. It's like you're multiplying just a weird kind of, I don't even know what to describe that shape. But you're just kind of matching these things together and matching those things together, if my picture makes any difference at all. So once you've done the first row, then you move on to the second row. So let's see if I can get my erasers out. There we go. So second row, I'm going to have the 6 and the -2, and then you go back to the first column. So I'm going to take the 6 times the 3 plus, and then I take -2 times -2. Once I've written that down, then I'm going to take that same row, but then multiply it by the second column. So I always start with the 6, and then that one's getting multiplied by the -4, and then -2 by the 9. And you might start to see a pattern forming here. Oops, I meant to get my highlighter, not my pen. Let me erase that. Let me go back to, let's try to do my highlighter. You might notice that if I color that first column yellow, you might see a little pattern basically. You're always going to be multiplying them in the same spot. So that's kind of a way to check yourself whether you're doing your multiplication together, because you are going to have a visual pattern of the numbers in parentheses are going to match. And then what changes are the numbers in front. So once you've written that second column, or the second row, and you've done both columns, then you move on to the third row. So that would be 5 and 4, and then you multiply that by the first column. So I have my 5 times 3 plus 4 times -2. So again, you can see that the 3 and the -2, those are just staying in those locations. The numbers in front that are changing are those row numbers. And then I'm going to take that last row and multiply it by the second column. So that's 5 times -4 plus 4 times 9. So once you've written that out, that's when you actually have to do that multiplication and addition. You're going to end up with 3 rows, 2 columns. And it's easy enough to just do on your calculator. -1 times 3 plus 4 times -2 for that top left. So that will give us -11. It's up to you if you want to write all the bottoms, like all the first column and then the column, however you want to do it. I'm going to just do the first column first. So then if I do the first column, second row, I have 6 times 3 plus -2 times -2. So that gives me 22. Then in the last entry in that column, I have 5 times 3 plus 4 times -2, and I get a 7. Then I can go to the next column. I have -1 times -4 plus 4 times 9. If I'm going to that top right, that gives me 40. Then I have 6 times -4 plus -2 times 9, which is -42. Then 5 times -4 plus 4 times 9, and I get 16. So now my final answer is a 3x2 matrix, 3 rows, 2 columns. You guys have any questions? Seems pretty easy. It is, once you've seen it worked out, then it kind of makes sense. It's just row by column. I think it's really hard when you're trying to learn it from the textbook and then you are like, what am I looking at? Like, I do want to pull up the browser. Actually, I gotta log into the classroom because I want to show you guys. I should have a link somewhere in the class of technology that you can use for this week for matrices. I believe it should be in the weekly content, but let me double check. Okay, yeah, so there's these extra videos. These are great There's Desmos and Rishish. They can both do matrix multiplication. These are just videos, but if we go to the supplemental materials, do I have a link to them directly? Oh, I thought I did. I thought I had a particular link to them. Maybe it's under tutorials. No. Okay. I thought I had given a particular link to them. I'll try to remember to send those out in like a email or an announcement. But rishish.com, so I'm going to just copy that. So we want the matrix one, so I'm going to just click here. And it has Gauss-Jordan elimination, which is great for solving. Yes, the week 3 video. I'm glad that you watched that. Or when I was grading today, I was like, oh, some people have not watched my intro. Yes, I do have additional ones in the week 3 video. Rishish is actually my favorite now that I've worked with it more. But it does do Gauss-Jordan elimination, but it also does matrix multiplication here. So I'm going to just enter in the actual, let's see, we started with a 2 by 2, and then, no, we start with a 3 by 2, and then we're multiplying by 2 by 2. So you can just fill in these numbers. So let's see, what were those values again? -1, 4, 6. What's nice is that tab works here just to go to different, each cell. And then my second matrix was 3, -4, -2, 9. So once you fill that in, you just hit calculate. And then assuming I didn't make any math errors, we should, yes, that matches. So it means I did my math right. So then that gives you the result of the matrix multiplication. So you guys are allowed to use this. What I'd want to see when you're like, showing your work is to show the actual matrices, like set it up. Let's see, there's a laser pointer here. So like show this part in your work, and then you can show this final answer. So you don't have to show this middle one because you can do that with technology. So I'm going to assume, that you use technology to do it. And I actually you could do it by hand, but you won't make mistakes if you use technology to do it. So I would just say use it because it's going to save you some pain, but at least you can understand what's going on here. And understanding this part will help you on that assignment answer. There's a question about interpreting what the multiplication means because it's in terms of real world, it's a real situation kind of thing. So understanding what numbers you're multiplying here will help you interpret. So it might be beneficial to do this middle step anyway, just so that you see what's going on and you're understanding what the numbers are meaning and what we're actually multiplying together. Any questions? Okay. Now I do have, if I can get my screen back pulled up. Okay. So I did want to do another one with a square to show you how you square matrices, because sometimes you won't have to do it on the assignment, but you might have to do this in your other courses. I know in engineering, in the electrical engineering courses, there's a lot of stuff that has to do with matrices. Oh, sorry about that. I somehow got disconnected. I don't know what happened. Let's bring back up there we go. Okay, not sure what happened there. So I wanted to do a matrix multiplication where you're squaring, because unlike regular numbers where you just square the number, when you do a matrix, you can't just square every part of the matrix. It doesn't work that way. You can't square each element. You have to do the manual matrix multiplication. So for a squared, you have to actually write this out and multiply. And that's because we have this addition part that's part of the matrix multiplication. And so that's why it doesn't work out where you're just squaring each element. So when I'm going to multiply these, I'm going to have my first row times the first column. So that's 3 times 3. So that part is squared, but then you have this -4 times -2. So that's the part that ends up where you're not going to end up with something that's just squaring. So then you take that first row and you're multiplying by the second column. So then you have 3 times -4 plus -4 times 9. Now notice none of those are like -4 squared. Like you're not actually squaring that part at all when you're doing that particular multiplication. So then I move on to second row, first column. So you have -2 times 3 plus 9 times -2. And then that last row, last column, -2 times -4 plus 9 times 9. So there's a 9 times 9, but nothing else in there ends up being squared. So then I'm just going to go top left. I have 9 plus 8, so I get 17. Underneath that, I have -6 plus -18, so that's -24. Top right, -12 minus 36, so that's -48. And then we have 8 plus 81, so we get 89. So you can see that a squared has no relation to actually squaring each element. Because normally when we square numbers, if we square a negative, we end up with a positive. But if you have a matrix that you're squaring, it's very different. You can still end up with negative entries. You know, none of those numbers are actually something squared. So that's the one key thing, is you have to actually do that matrix multiplication. There's no real nice shortcut to that. Now the last slide here is just basically the procedure for solving a system with matrices. And this is actually covered in the 8.1 video that I have in the classroom, but I didn't write it out step by step. So here I'm just basically writing out step by step using the language we've been using. So first you have to write matrix A, which is just the coefficients in front of each variable. And then you're going to have X, which is just going to be our unknowns. And then B is the constants, what the numbers are equal to with your system. And then what you do is you're creating one matrix, and you have a little colon there. That's sort of taking place of the equal sign. So instead of writing an equal inside a matrix, we just have little colons. And then you do the Gauss-Jordan elimination, or sometimes it's just Gaussian elimination, depending on, they're basically the same thing. And then I showed you that was on that reshish, that there's that the link for doing that. And what happens is your result is going to have an identity matrix before the colon, and then the numbers on the right side are going to be your actual answers. So this is just writing down the procedure, but the actual solving, I demonstrated that in my 8.1 video. So this was basically everything that I wanted to cover for you guys. 8.3 starts going into inverse matrices and determinants and an alternate way to solve. You do not have to use that method to solve if you don't want to. You can use the Gauss-Jordan elimination and use technology to solve and do it that way as well. And there's nothing on the assignment that requires you to do inverses. So that's why I decided not to go into that stuff. So do you guys have any questions for me? All right. Well, if you guys do end up coming up with questions, or if you're not sure if you're showing enough work with using technology, you can email me and let me know. And I can definitely show you what you need to do, or let you know if, oh, you need to show more work here. You know, you can just send me a screenshot of whatever you have, or you know, a picture or something like that, and I can take a look at it and let you know if you need to show more work or not. But I strongly encourage you to use technology to solve the matrices in this week so that you don't have any math errors, because there are a lot of moving parts and it's really easy to make a small mistake, especially, you know, if you have 3 variable systems like the week 2, there was that 1 3 variable system, and it's so easy to make one mistake and mess everything up. So I strongly encourage you guys to use the technology for that. So that's it. Thank you guys for showing up and sticking around while I got kicked out of the room and came back in. So I really appreciate it. I will try to get this out tonight. If not tonight, it'll be out tomorrow. I should still give you guys some plenty of time to work on the assignment. So yeah, that should be it. I've already graded all of your assignments, so you should have the feedback from there. Again, with the systems, make sure you're writing your systems before you turn into a matrix, so that way I can make sure that you're doing it correctly, taking your system and turning it into a matrix correctly, that you have all the numbers in the right places. So and make sure you're answering your questions with a sentence, so that I know. If you just tell me x equals 2, sometimes, you know, depending on how you labeled your variables, you can label it anything you want, so I don't know what x is. So make sure you're following that up with a sentence, and I think that's everything that all the tips I have for you guys. So all right, I will talk to you guys later. You guys have a great night.